Hi everyone, what's up? Today I want to discuss what a differential is. To explain what differentials are, I'm gonna go way back to the beginnings of calculus, to the most basic concepts in calculus, and say something about the difference quotient. So we know that we define f prime, the derivative of any function f, so f prime, we say it's always the limit, as I'm gonna use delta x notation, so as delta x approaches 0 for the change in f, which is gonna be f of x plus delta x minus f of x, and this divided by delta x, okay? Now, we can also write this as the limit as delta x approaches 0 for the change in f over the change in x, okay? This is just simply going to be the numerator for the difference quotient is just the change in the f values. So you can write it using delta notation. And we also say that, well, this could also be the same as the limit as delta x approaches 0 for delta y over delta x, okay? Usually, we just use y and f interchangeably, okay? We say they're the same thing. In the xy plane, if you let y be equal to f of x, well, that's why we use delta y to represent delta f, okay? Now, all of these are just, a lot of ways, a lot of different notations, including f prime. All of these are different ways in which you can write the derivative for any function f, okay? The derivative of f with respect to x, okay? But I'm still missing one very important notation, and that is Leibniz's notation, and that is where differentials come into play. So this notation right here is probably going to be, I would say, the predecessor of differentials. So when you have this limit right here, you could also write it like this. So that is the same as dy over dx, okay? The change in y, we know is going to be a very small number, okay, because we're taking the limit. And we know the difference between the subtraction between these two values is going to be a very small number, and that means that delta y is also going to be a very small number. We represent very small numbers for a particular variable using d, okay? Just normal alphabet d, okay? So the limit as delta x approaches 0 implies that delta y will be a very small number, and that is where Leibniz's notation is used to represent that limit, okay? D simply represents the limit as y is a very small number, okay? And dx, well, represents the limit as x is a very small number, okay? That's, some intuition into the definition of dy and dx, okay? And, well, that definition comes from the difference quotient, okay? Now, differentials are basically the numerator and the denominator in this fraction, okay? So, how should I put it? So, we know dy over dx is also going to be f prime of x, okay? You have this whole chain of expressions, and at the beginning, well, we said that was equal to f prime, and, well, of course, it's pretty, you've seen that dy over dx is what we call f prime of x. So, when we say what is the differential of y, we're asking how can we compute a very small value of y, okay? Now here's where we need to consider a bit of ambiguity. There's not a very exact definition for differentials. Some people say it's going to be a very small piece of a y value, okay? Some people say it's going to be the limit as y approaches 0 and the limit as x approaches 0. All those are very valid definitions, although you could create a different, you could have a different perspective on how to interpret those definitions. But something that is very that has been well established and that everyone agrees on is that dy, the differential of y, we call it dy, okay? And in order to compute the differential of y, you're going to treat dy and dx as ratios, okay? As simple numbers that you can play with, okay? So dy over dx is going to be a ratio of two numbers. So we say that dy over dx, if you're going to compute it, well, you can move dx to the other side of the equation, just as normal algebra, and you have f prime of x times dx, okay? And this is how you compute the differential of y. Now I believe you can see probably some resemblance with a linear function here. If you say y is equal to m times x, where m is the slope, well, I think there's a bit of resemblance here. So the way I like to think of it is that a very small value of y, the limit of y, as y approaches 0, a very small value of y will be equal to a very small value of x times the rate of change, okay? That's, one interpretation you could use to to understand the differential of y, okay? And of course, you could also have the differential of x, okay? And dx, since we're treating this fraction as a simple ratio of two numbers, well, you could say that dx is going to be equal to dy divided by f prime of x, okay? So this is the differential of x. Now in integration, especially in u substitution, you use differentials a lot. You cannot use u substitution without using differentials, basically. So yeah, this notion is very important. It's very important that you understand this notion, okay? And I think, well, one thing you can do is, use this y equals mx idea, okay? So now I'm going to give you some examples of how you can compute differentials for different functions. So let's define a function y. Let's just say that y is going to be equal to 10x squared plus sine x, okay? Let's say this is our y function. Now we can ask, what is the differential of y? Well, you could write dy is going to be equal to the differential of the function, whatever y is equal to. So you have the differential of y is equal to the differential of 10x squared plus sine x. And we know this will be equal to, so we know it's going to be f prime times, or y prime in this case, f prime times dx, okay? Now f prime is going to be this is going to be this expression, so now we just need to take the derivative of these two terms, okay? So this is going to be 20x. By using the power rule, you can get 20x for the first term, and we know the derivative of sine is going to be cosine x, okay? And you need to be careful, you need to write a parenthesis because it's going to be the derivative times the differential of x, okay, times dx. Now, you could also write this as the following. You could simply distribute dx to each of these values, okay? Remember, dx is basically a very small quantity of x, okay? So you can, well, if this is a normal quantity, a normal number, you can treat it as a coefficient, as a factor, as anything you want, as anything you would, as any type of number that you would deal with in normal algebra, okay, and not in calculus. In elementary algebra, you can distribute this coefficient to these two terms, okay, and that is something you can do. So you can say that 20x times dx plus sine x times dx will be equal to the differential of y, okay? So this would be how you can compute the differential of y. And now you could also ask, well, what is the differential of x? The differential of x is going to be the differential of y divided by f prime, okay? Or y prime in this case, which would be this function right here, okay? So that would be one example. Now let me give you another one. So what if we have, let's define y to be equal to sine x times tan x, okay, tangent. Now what is the differential of this function? Once again, we could say that dy, the differential of y, is going to be equal to the differential of sine x times tangent x. And we know this will be equal to, we take the derivative of the function, we need to use the product rule here. So I'm not gonna change sine x. So we have sine x times the derivative of tangent, we know it's gonna be secant squared. So secant squared plus, now tangent, I'm gonna leave it as a coefficient, or as a factor, I'm not gonna change it, times the derivative of sine x, we know that it's gonna be cosine x, okay? And of course, you can't forget, this is gonna be parentheses times dx, okay? You cannot forget the dx, because this would be the entire f prime term, the entire f prime factor, I'm sorry, and you need to multiply it by dx, okay? Now you could, if I'm not mistaken, you could simplify this somehow. This would be 1 over cosine squared, so that would be tangent times secant. So this would be tangent, so we have tan x times secant x times the differential of x. I'm just distributing dx, so let me confirm that. Yeah, that would be this term. And now this, remember, tangent is equal to sine over cosine, and you have cosine here, so this would just be sine, okay? So this would be plus sine x times dx, okay? And this would be the differential for sine x times tan x, okay? So that would be the entire thing. This is the entire video. This is not a very complicated topic in terms of, the methods, the mechanics of taking or of finding a differential. It's nothing too hard. You just need to know differentiation rules, and that's it. And understand the notion that dy over dx is basically a fraction. That is a very interesting debate in math. And I'm on the side that yes, fraction the dy over dx is a fraction because well you're basically treating small values of y divided by small values of x. Okay, so you can treat those numbers as fractions as no as normal numbers, and you can move dx to the other side of the equation to find dy and so on. Okay, so that's been the entire video. I hope that you enjoyed this video, you learned something, and see you in the following one. Bye.